So here I have a track, a wooden track that two marbles will go down. You watch. So 2 marbles will go down this wooden track. My question for you guys is, which marble will win the race? Which marble will hit the end will hit the end first? Goodness, I could not find my button. There we go. Okay, so don't shout it out. Just want you to think which one will hit the end. Which one will hit the end first? All right. I actually will put this video recording up, which is nice for you guys to have. So now you guys have a big view of what's happening. All right.
Awesome. So
which one is hit first? So we'll talk about this as the left track and the right track. So we'll call this one the left track, and we'll call this one the right track.
No.
Backwards.
Yeah.
Here, we'll do this then.
Really?
No, now you can't even see when
Is that
they hit
better now?
You can't see when they hit.
Can't see when they hit now? Okay.
Right.
All right. Then we'll call this one track 1, and we'll call this one track 2. Is that better?
All right. You guys, shut up.
Okay. So I'll even draw on the board for you guys. Okay. So track 1 is this one. Track 2 is that one. All right.
Just draw it.
So 1.
Can you show it to
2.
us to the side so we can see what to draw on the paper?
Yeah. You want to see the side view? Yeah. Here's the side view.
What is this unit?
This is still Unit 6.
But what is it?
Work energy theorem.
No, like this chapter. What should we label?
Chapter 11.
Wow.
No paper left.
I know, I just got plates.
There's no paper left?
Right here.
Not in the back.
Okay, there's some right there. Okay. Yep, I have none in my stockpile. No, you're fine. We have some right there. All right. So track 1, track 2. Track 1 is the curved track. Track 2 is the straight track. So which marble will arrive at the end first?
Same time.
Same time.
Same Rick says same time. Nan says same time. Is that when you said same time?
Oh,
I did.
Same time. Okay. Who says they hit at the same time? Raise your hand.
I just want to go
Okay.
there.
Okay. Who says that track 1, the curved track, will hit first? Okay. Who says that track 2, the straight track, will hit first? Okay. Who doesn't know? Who doesn't care?
Oh, this is why mine gets.
Mine, the only 2 hands don't care. Wonderful. Okay. All right. So we'll try this out. Now this little E-shaped mechanism is to just make sure I release them at the same time. Okay. So there's our 2 marbles. Can we all see?
Jorge is away.
Okay. Jorge, get out of the way. Okay. Ready? Okay. Come to the fence. Okay. Crouch down though so you don't block. Ready? 3, 2, 1. Which one hit first?
I didn't see.
You didn't see?
I didn't see it.
Well, maybe
Yeah.
the screen is a little light.
I feel like the
I didn't expect it to bounce back.
Ready?
I'm talking about the video.
The video is a little laggy. So 3, 2, 1.
The curved one.
Track 1.
I think they both
Dang,
did
I
at the
was
same
right.
time.
The curved one.
It just bounces back.
Yeah, it just bounces back. So
All right.
maybe got a bounce back.
Let me try to release some Rex. We'll go one more time.
Okay.
Ready? 1, 2, 3.
The curved one.
Which one hit first?
One.
The curved one.
Oh.
So the curved one hit first. What does that tell us about the curved one then?
It's faster.
Word.
Steeper.
Caleb, what'd you say?
It's faster.
It's faster.
There's more power.
Has more power.
Less time.
It is more powerful.
Yeah.
Takes less time, right? Finishing your brain with the idea of power. We'll come back to that in a second. So, Caleb, you said it's faster, right?
Yeah.
More kinetic.
Okay. Now, when you're saying faster, do you mean instantaneous velocity or average velocity? Okay, Caleb says that when he says faster, he means average velocity. Okay? So, let's ask a question about the instantaneous velocity then. Down here at the end of the track, which track has a higher instantaneous velocity? The curved track or the straight track?
Track 2.
Okay. Who thinks the curved track has a larger instantaneous velocity here at the end? Raise your hand. Who thinks the straight track has a larger instantaneous velocity here at the end? Okay. Now, a lot of you didn't vote. Why didn't you vote?
Because they don't know.
Because they don't know, so that's one option. What's the other option?
They don't
Because
care.
they're the same.
Is there a different option here?
They don't
Yeah, they don't care.
They don't care? Okay. Is there another option?
Well,
They're the same.
where?
They're the same. The other option is their instantaneous velocity the same? Who thinks it's the same?
Well, where are you talking about?
At the end, the instantaneous velocity right here at the end.
No.
When they hit.
No, because that one hits first. It's the same.
It hits first, right? But are we talking about average or instantaneous there?
Instantaneous.
Talking about instantaneous? So, the fact that this one hits first, okay? Guys, the fact that the curve track hits first is a product of the curve. So, can we all see this?
Yeah.
Go this way with it? Okay. Oh, there we go. Almost
Oh
broke it.
my gosh.
Almost broke it. Breaking stuff. Okay. So, the curve track. The reason why the curve track hits first is it has a much steeper slope, right?
Show do.
So it has a greater acceleration.
Show do.
So it reaches its maximum velocity here, right? Whereas this one reaches its maximum velocity where? At the end, okay? Because it's accelerating the whole time at the same rate. Where this one accelerates the whole acceleration all at once and travels at that velocity until it gets to the end. So that's why that one reaches the end first. So the curved track has a higher average velocity, right? The straight track has a less average velocity. But the question I'm asking is the instantaneous velocity here at the end. Okay? Now, if we look at the tracks, okay? And a little bit. And then we'll catch a glimpse of Rex's foot. Here we go.
Oh no, you
Okay.
couldn't see my foot this whole time.
You could? You've been moving your foot back and forth?
I've been throwing up gang signs and everything.
Thank you, Rex. I appreciate that. All right. So, if we look at the two tracks, what can we say about their starting heights and their final heights?
Same.
It's the same, right? The starting height and the final height are exactly the same, right? Now, what force propels the marbles
Gravity.
down the track? What is it? Gravity. Which way does gravity pull?
Down.
Okay. Gravity is a vector that points down, right?
Show do.
Points straight down, doesn't it?
Show do.
Now, what part of their displacement is in the same direction as gravity?
The up and down.
The up and down, right? So the distance from here to here, that's the part of the displacement that are in the same direction as gravity, right? So the distance between the displacement between their starting point and their ending point, that's the part that's parallel to gravity, right?
Yeah.
But now what can we say about those two displacements?
You know.
They're the same.
They're the same, right? Those displacements are the same. Now, do you think these two marbles are different masses?
Nah, they're the same.
Okay. To prove to you or not, we're going to take the marble from the curved track and put it in the straight track. Take the marble from the straight track and put it in the curved track. And we'll do the same thing. And Whitney, we get the same result.
They're steel ball.
Okay.
Tape.
Steel ball bearings.
That's it.
All right. So the exact same result, regardless of which marble goes where. I can't find it right now. Okay. Do you need a stapler?
Is that dog food?
No, my hair is stuck in
No.
the
Okay. So, any questions?
Isn't it back there?
It is back there. Thank you.
Uh,
Any questions, guys?
no.
No questions.
No, sir.
All right. So, if they have the same force of gravity, the same displacement, what can we say about the work done by gravity?
It's the same.
It's the same, right? If gravity does the same amount of work, then what does that mean about the energy the two marbles have here at the end? What do you guys think? If gravity does the same amount of work, then what does that mean about the energy the two marbles have at the end of the track? What is it? Someone said it. The same. Good. Okay? Because work is the change in energy. Okay? So, to prove to you that they have the same amount of energy at the end, okay, we're going to look, and we're actually going to figure out the final velocity of the marbles at each location. Okay? So, yeah. All right. So we're going to figure out the final velocity of the marble at each of the two locations. Okay. Now, the marbles, okay, the marbles have a mass of 0.5 kilograms. Or not 0.5. 50 kilograms. Okay. The marbles have a mass of 50 kilograms. Oh, wow. 50 grams.
Big ol'.
Goodness. Those are huge marbles. All right. 50 grams. Wow. Okay.
That should be like 10 grams.
So the mass is 50 grams. Okay. What's that in kilograms? And I wrote kilograms again.
0.0.
Good. 0.05 kilograms. I don't have to worry about writing the wrong units because now we know. The mass of the marbles is 0.05 kilograms. Right? Straight track. Curve track. Okay, and it does dip down and come back up just a little bit. All right. Yep. 2 marbles. Okay. And down this way. Now, what are the forces acting on these 2 marbles again? Gravity. Which way does gravity point? Down. So on both marbles, gravity points straight down, right? And that force of gravity is the same for both. That force of gravity equals mg, right? So 0.05 times 9.8. What does that equal? I can do it in my head. 0.049.
You're so smart.
Well, half of gravity is 4.9. And then you move two spaces to the right. 0.049. Yeah. Okay. Any questions? Does that make sense, guys? So the next thing to worry about is the displacement. Now I've already measured the track. I could go through it again with you if you want me to. But the height here is 15 centimeters.
Go through it again.
Okay. The height here is 6 centimeters. Okay? And that's above the tabletop. Okay. So can we figure out their displacement? Good, 9 centimeters. So the displacement of the marble, the distance from there to there, right, is 9 centimeters. How many meters? 0.0. I was going to use the same voice. 0.09 meters. What do you tell me? Is it 0.49? Ah, what happens when I do things in my head. Thank you, Caleb.
What?
Really?
Yeah.
Did you just call?
No, Caleb said, you're so smart earlier. I know Cassandra's the one that told me.
I was gonna say what?
Okay. Cassandra, thank you for correcting me. Caleb, you jinxed it by saying I'm so smart.
You're welcome.
Oh, idiot. Me, not you.
Hey, and it's on recording so we can watch it.
And I can watch it again and again and again. And
It's like,
all right. Any questions? Thank you, Cassandra. Guys, any questions?
wow, I have to erase now.
Yes, I could say
No, you don't. You just have to put a dot down. Okay. Any questions about the force and the displacement?
I'm not thinking.
No questions? So can we find the work done?
Yeah.
No.
We just need to use one of these fancy equations that are wrote up in the book.
Okay. Work is the product of force and displacement, right?
Yup.
So can we find the work done? Yeah, what is it?
6.
Keep going, Caleb.
0.49.
0.49 times
6.
0.09, good. And what does that equal?
A number?
A number. Thank you, Rex.
Is it close to 6?
Very well.
No, it's not close to 6.
0.1. 30. 40.
Guys, you have calculators.
40. Hold on, let me do it.
No, we don't. Our school doesn't provide us with them.
Rex, your calculator's right in front of you.
No.
Okay.
44.1.
People of YouTube
Oh,
save
that
us
was
in
pretty
school.
Oh, goodness. Rex, you make me laugh.
Donate. So.
0.0441?
Yes.
Hey,
Yes,
I
of course
told
you're
you.
right.
Wow, I said
There we go.
You are so
0.41.
wrong.
Okay, there you go. 0.0441 joules. Does that make sense, guys?
Keep
Yeah.
erasing.
Are there any questions? Well, if you just punch in your calculator, you wouldn't have to erase anything.
No, I want
Okay.
to trust my teacher.
Any
Right?
questions? I'm doing this in my head. I don't have my calculator out.
Why are these pants so short?
We just like to make you feel good.
All right. Thank you. Thank you. I get the same joy with you. All right. Any questions about this work done?
No.
My pants are short.
Okay.
Get it.
Guys,
Mine are short. I'm fine.
ladies, gentlemen,
Kyle, get my
This is
paper.
long too.
guys, thank you. All right. Any questions?
No.
Are we
No
done?
questions? No, we're not done. Okay.
Are we done?
So, what force did this work? Gravity. Okay? Gravity is inside this system. Okay? Now, when I put the marble at the top of the ramp, okay, I worked against gravity, right? And me putting the marble at the top of the ramp, that'd be an example of an outside force, something from outside the system doing work. Okay? Gravity is actually inside the system. Gravity is what increases the energy of the marble as it rolls down the ramp. Okay? What type of energy does gravity increase?
Kinetic.
Kinetic, good. Because as the marble rolls down the ramp, what happens?
You know,
Speed lines are supposed to be the hand.
velocity increases.
Velocity increases, right? So that means, gentlemen, okay? So that means that the work done by gravity is equal to the change in kinetic energy.
Hey, this was on our
So work equals change in kinetic energy. So that's part of the homework that I was assigned yesterday. Right? Now,
Whatever.
what does change mean?
Like when you take one kinetic energy minus
The F
Which one goes first?
F minus initial.
Good. Final minus initial, right?
Yeah.
So this
I
equals...
knew what I was talking about.
I know you did. So now that's the only equation I'll give you. W equals change in kinetic energy. But what we need to know then is change means KE final minus KE initial.
Yep.
That's what our work equals. Right? And I can start plugging in the rest of KE because we know that kinetic energy is equal to 1/2 mv squared. Good. So KE equals 1/2 mv squared final minus 1/2 mv squared initial. Now you'll notice I only put F and I on the V's because they're the only thing that'll change.
Yeah.
The mass of the marble does not change as it rolls down the ramp.
Show don't.
Okay? Does that make sense?
Show do.
Okay. What? Oh, it's just my sloppy handwriting. Any questions? This makes sense. So now what can we do here? Can we find the final velocity of the marbles?
I mean, Theo.
Theoretically. I was waiting for that to come up, Rex.
But we don't.
What's the initial velocity of the marbles? 0. So V initial up here is 0, right? V final down here, that's what we'd like to find.
And with you leading us, we can find anything.
Good. Okay. So,
That's not our test.
what's this right here? Work. Where does this go? Into the W, right? So 0.0411 equals 1/2. The mass of the marble is 0.05. Velocity. Final, we don't know. Thank you. I was looking for it. Minus 1/2 times 0.05 times 0. Don't forget to square 0, right? Okay. What does it become? Third time in the annoyed voice. 0. Okay. So this part right here becomes
0.
0. Okay. What I made that mistake there, Cassandra?
Isn't it 0.0441?
Is it 441?
Yes.
Yeah.
Goodness.
We told you that, remember?
You did tell me that?
Yeah.
I told you that.
Okay.
You didn't-
0.0441. My goodness.
Thanks, guys.
It's okay.
You take a 2-day break because you're sick and you come back and you're just off.
Yeah.
It's okay.
You know.
That's how I feel on the weekends.
How you feel about the weekends?
So we
Sorry.
should.
And I always come in on Monday morning and just make you work, right?
Yes.
Sorry, our teacher
Evil.
wasn't good.
I would hate
I
to
know,
have
I-
the first hour.
Sorry. Okay. So 0.0441. No, first hour I didn't make any mistakes. I should have filmed then. All right. So what's this equal? 0. So 0.0441 equals. I'll do this in my head correct. I gotta redeem myself. And I won't be offended if you check it. Just to make sure.
Why is that necessary when
Okay.
you have the water?
So now what do we do? What do we do? Okay. Divide by 0.025, right? So 0.0441 divided by 0.025, what do we get?
1.764.
1.764. So that's their velocity or no?
No.
No.
No, what do we do now?
Square root it.
Square root it. Don't forget to square root it. So square root 1.764, and I guess it's 1.33, am I right?
It's 1.3281566617.
1.33.
Get them out.
Hey, I remember one thing, right? There we go.
It's really
So,
1.3.
1.33, it's 1.3285, so we round to 3. Okay,
8 rounds and 2.
to 3. Okay, so the two marbles have the same instantaneous velocity. Now, if you're saying, but Mr. Branch, I don't believe you because there are two marbles and you only did one equation. Is anybody thinking that right now?
Yeah.
Okay, well, remember leading up to this, we said that the thing that increased their kinetic energy was gravity, right?
Yeah.
Gravity applies a force over displacement. We know since the two marbles start at the same height and end at the same height, they have the same displacement. Because they're the exact same marble, that means they have the same force of gravity, right? So the work done by gravity is the same on both. And since the work done by gravity is the same on both, we can use this equation to find their final velocities. Does that make sense, guys?
Yeah.
Seems simple enough?
Sure do.
Now, this idea, work is the change in energy. That's a concept we need to hold on to. Okay? Like I said, I will not give you the rest of this, so you need to know how to plug in the finals and initials.
Why would you not?
Because I want you to know what delta means. I'm a mean guy, Rex. That's why.
Okay.
Now, is kinetic energy the only energy involved in this situation? What's PE, non?
Potential energy.
Potential energy, good. So, work equals kinetic energy, change in kinetic energy, but how does it relate to potential energy?
Well, because
It's the total.
Well, let's take a look. So, let's look at our change in potential energy.
It's nothing.
Okay? So, change in potential energy, we'll do this one in blue. Delta PE equals PE final minus PE initial, right? Right? Now, for potential energy, what's the equation?
Mass. I mean, gravity height.
Mass, gravity, height, right? PE equals mgh. Now, which quantity there will change? Rex, stop talking, please.
I'm trying to correct the clock.
Okay. Which quantity there will change? Mg or h?
H.
H. Mg stays the same, right? Mass times gravity the whole time, right? Mg stays the same, doesn't it? The one quantity that changes is the height. So this ends up being mgh final minus mgh initial. Okay? So what was our final height?
Why are you stating that?
6 centimeters.
6 centimeters, right? So our final height is 6 centimeters, which is 0.06 meters, right? Our initial height was how many centimeters?
15.
15 centimeters, or 0.15 meters,
Yeah.
right? That was our initial height. Can we find our change in potential energy? Because we know mass is 0.05. We know G is 9.8, right? So we can find our change in potential energy by doing 0.05 times 9.8 times 0.06 minus 0.05 times 9.8 times 0.15.
Oh my goodness.
If you want to factor out common terms and distribute or reverse distribute, that's fine. It's up to you. Or just plug it all in. And what do we get?
We're just not doing
What do we get, guys?
What do we get?
6. I'm still writing
6.
it down. Give me a second.
6.95.
No, you don't.
You get negative.
You didn't even do the problem.
You get negative.
I did it in my head.
Negative 0.0441.
Why can't
It's
it be
the same
6?
thing but negative.
Wow.
Oh my gosh, it is.
You could have just said that.
What does that mean?
I didn't
But
notice that.
Now you remember that
What is that?
this change in potential energy is the opposite of the work done
You may just write this off.
from kinetic energy, right? So that change in potential is the opposite of the work done, right? Does that make sense?
Nope.
No?
Yes. Yes, it does.
Well, let's think about it this way. This right here, 0.0441, this equaled our change in kinetic, doesn't it? Right? This negative 0.0441, that was our change in potential, right? So what this shows us, and this is kind of a big deal, is that our change in kinetic energy equals our negative change in potential. Okay? So what that means, thank you, Rex. What that means is as potential energy is losing joules, kinetic energy is gaining joules.
Wow.
So that they're inversely related. As one goes down, the other one will increase, go up. Okay?
Wow.
Does that make sense?
Yeah, it does.
Now we're
But
done.
what it doesn't make sense is why you had to go through all that to explain.
Because it's proving it to you.
Actually, it proves that.
Gracias.
Now, what's the relationship, guys? What's the relationship between work and the change in potential energy?
It's
Well, repeat that.
negative.
What is it, Omar?
It's the opposite.
The opposite. What do you mean?
You
Yeah,
mean
it's
the
negative.
joules were 0.0441.
It's a negative.
And the change in potential energy is negative 0.0441.
So would you agree with this equation?
Yes.
Yeah. So work equals the negative change in potential energy. Okay. Does that make sense, guys?
It does.
Okay. Now, you're probably saying, well, work equals negative change in potential energy. How does that make sense? Okay, well think about it. As gravity pulled the marble down, did the potential energy increase or decrease? As gravity pulled the marble down, did the potential energy increase or decrease? Decrease. So gravity did positive work. Potential energy decreased, right? Negative, negative makes the work a positive. So it works out that gravity is still doing positive work. Does that make sense?
Sure.
Okay. Now you can also think about it. If I take the marble and I raise the marble to a certain height, what am I working against? Gravity, right? So which way is my displacement vector as I lift the marble? Upwards, right? Which way is the gravity vector? Downward, right? So what kind of work does gravity do in this case? Negative, because I have an upward displacement. Imani, okay? Okay, I have an upward displacement and a downward force, right? So the work done by gravity is negative, right? So the work done by gravity is negative, and our change in potential energy, did I increase it or decrease it?
Increase it.
I increased our potential energy. So then those two negatives will cancel out and store energy in our system. Okay?
So is this like an
Nope, it's not an equation for it. Right? So, do these change in energies, do they make sense?
Yeah.
Yeah, are there any questions about that?
No.
Okay. So the two equations in boxes, the two black equations in boxes, W equals change in kinetic energy, W equals negative change in potential energy, those are equations that I'll give you. Okay? But you need to know how the rest kind of fills in. What?
What equation are you